Okay, yes, hello and welcome everyone, and welcome to the second day of ThinkyCon. I'm Ivan Koswara, also known online as ThinkyCon, and I'm going to present mathematics for puzzles 2. And you might be wondering why 2, because I did present 1 last year. And as as mentioned, maybe we will have 3, 4, 5 in the future, we will see. So just to be quick about me, I'm not a game developer, I'm still not a game developer. And I'm more a logic puzzle writer. So I write logic puzzles like this, things that you might find on books. And I have a logic archive on my website if you want to look at what kind of puzzles that I write. And well, last time we talked about the background, the motivation of it, so I will just keep it brief. We talk about like how puzzles are used in math. We know that puzzles are used in math, used for problem solving, for deductions, and so on. But we can also see math is used in puzzles by like some kinds of theory, some kinds of theorems, results, or whatever, find applications in puzzles. And last time I talked about several examples. This time I will talk about even more examples. And it will only be about examples. I will just let you admire and appreciate them. And if you have any questions, please ask them on live chat or on Discord. If we have time, we will get into some of the questions at the end. And even if not, I will continue to be around on Discord. So let's get into it. What we want to talk about is the Jordan curve theorem from the field of topology. So what does this theorem say? It says every simple closed curve has an inside and an outside. So I think you can think of what a curve is. It's just a line you can bend, or it can have turns or whatever. Closed just means it doesn't have loose ends. For example, it's a nice circle like this, or it looks something a bit strange like this, but there are no loose ends. It's closed. And simple just means there is no self-intersection. And what it says, every simple closed curve has an inside and an outside. You will think that this is a very obvious statement. It turns out it is not obvious in mathematics, mostly because there are some really cursed curves. For example, here we have the curved snowflake. You start with a triangle, and then each side you place a smaller triangle on it, and then again, and snowflake actually goes on infinitely. This only goes for 4 iterations. You just keep going 5, 4, 6, 7 iterations and going infinitely. You might imagine the curve looks really strange, but it is still closed, it is still simple, it still has an inside and an outside. And the reason this is not obvious is because things like this. But for our purposes, our curves are going to be nice and simple. So it's actually not too difficult to prove. So let's get into our puzzles. Our first puzzles. This is a puzzle genre called Yin-Yang. Here the puzzle is on top and the solution is on the bottom. And the goal is to shade some cells black, like this one. Here some of the cells are black. The black cells are connected side to side, and the white cells are also connected side to side. It might not be very obvious from here, but there is also another rule. There is no 2x2 area that is of the same color. And you might see some circles here. They just say black circles are black, the white circles are white. And if you feel like you are familiar with this kind of puzzles, that is probably because you saw this in Islands of Insight or some other kinds of puzzle games. I guess Islands of Insight have a lot of logic puzzles in general. But for this talk, we will focus only on the second and third conditions here. The black cells are connected, the white cells are connected. Now, let's imagine we have a purported solution for it. And there is a 2x2 checkerboard pattern, like here in the middle. What happens in this case? Let's take a look at the black cells of this 2x2. Now, the black cells are connected. That is a rule of Yin-Yang. So we can draw a path through the black cells connecting these 2 cells. And then we can draw the diagonal along the 2x2. And what by Jordan curve theorem, it says there is an inside, there is an outside. This is a problem because now the white cells are separated. One of them is inside the loop, one of them is outside the loop. They cannot be connected together. The black cells separate them. So that is a problem. And in general, this means there is no 2x2 checkerboard pattern anywhere in a solution of Yin-Yang, because we end up with this. And it's worth noting that this no checkerboard rule is not part of the rules of Yin-Yang. It comes from our deduction. We analyze the rules and we realize that this tells there is no checkerboard. It arises naturally. So let's take a look at another example. Let's take a look at the outer border of the grid here, and here we have some black cells on top and some black cells on the bottom. Again, the black cells are connected. We can draw a path along them. And now we circle through the outside, because this is on the edge of the grid, this is on the edge of the grid, we can connect them outside. And again, closed curve has an inside, has an outside. So the white cells are going to be separated. The white cells to the left of this path are inside the loop. The white cells to the right are outside the loop. They are separated. They cannot connect to each other unless there is no white cell on one side of the grid. So there's no white cell inside or there's no white cell outside. In other words, this black path must be along the grid. This comes into the border rule. All the cells of the same color, all the cells of black cells here are contiguous with each other. Here you can see the black cells are contiguous along the border, the white cells are contiguous along the border. And again, this rule is not something that is explicitly stated in the rules of Yin-Yang, it's something that arises naturally. And if you want to solve Yin-Yang puzzles, you need to know no checkerboard rule, you need to know border rule, because it is used so much. And let's take a look at another example. Here's a different puzzle genre called cave. We draw a loop along the grid lines, non-intersecting loop, so it is a simple closed curve like this one. Here's the green loop is the solution. The black cells just say what's outside the loop. We will get into that. And then there are some additional rules about the numbers. For example, all the numbers must be inside the loops. Each number tells how many cells are visible. I won't get too much into that. I want to talk about the loop. So the interesting thing about cave is that in logic puzzle community, some people don't like to use loops for cave. They want to shade cells, I feel, because it's more natural for them. And if you turn the loop into shading, you end up with something like this. You shade some of the cells black. The white cells are inside the loop. They must be connected. The white cells are connected. The black cells, the part that are outside the loop, must connect to outside the grid. And you might think of it like, if the black cells are inside the grid, that means you have a loop that defines these black cells and a larger loop that defines the white cells. And so you end up with a loop inside a loop. And that cannot happen. That is why the white cells are connected, the black cells connect to outside of the grid. And also rules like all numbers must be inside the loop becomes all numbers must be white. So I want to talk about this because now let's take a cave solution and make the entire outside of the grid black. Again, the white cells are connected, the black cells connect to outside of the grid. That means the black cells now connect to each other because the entire outside is black. Remember, white cells are connected, black cells are connected. We had a result from Yin-Yang, and that does not actually use any special rules about Yin-Yang. That just relies on white cells connected, black cells connected. That means we have our results as well. No checkerboard rule also applies here. And you might ask what happens about the border rule. Well, the border in this case is just the black cells that we added. So the entire border is already black. It's already contiguous. We don't really have any new thing about the border rule. But the not 2x2 checkerboard rule is important. It also applies in cave. So you can see Jordan curve theorem somehow finds applications like this. And also these kinds of rules don't come up in the actual written rules of the genre. You just end up with these rules, these results naturally. Let's go back to Jordan curve theorem, and this was a statement of Jordan curve theorem. We have a corollary, which is basically a related result. If two curves always make clean intersections, they intersect an even number of times. I will explain what clean means later. So what does this look like? So imagine our two curves from earlier, one nice circle and one very strange curve. Now these two intersect with each other. You can count how many intersections they have, and turns out there are 8 intersections in this case. This is an even number. Now, why is this true? Can we prove this? The reason is because of parity. And if you were here last year, you remember me talking about parity quite a lot. And turns out it is a very useful concept in mathematics. It comes out even in here. And the idea is if you start from anywhere on this red curve, let's say starting from here, you are outside. And then you cross an intersection, you get into the inside. You cross the intersection, you go to outside, and so on and so on. And at the end, you must loop back in here. You must be outside again. That means you must change sides an even number of times. And that means an even number of intersections. And when I mean clean intersections, that just means when you make an intersection, you must actually change sides. You cannot have something like you just make an intersection, but you just brush the other curve. It's just a tangent. That does not count as an intersection. So let's apply this in more puzzles. This is a Masyu puzzle, which is again draw a non-intersecting loop. Again, this is a puzzle on top and solution on the bottom, draw an intersecting loop. And here you can see black circles, white circles. They tell you how the loop behaves. And the rules are kind of complicated. On white circle, the loop goes right. And also it turns before or after or both. On a black circle, the loop turns, but it goes strike both before and after. So even if you look at these rules, the rules are not very symmetric. On white, it says turns either before or after. On black, goes strike both before and after. So it's kind of weird, but we get used to it. And this is a very popular genre in logic puzzles. And strictly speaking, when you talk about Masyu, you actually usually present it on this kinds of grid. The loop is on cell centers instead of grid lines, but I find it personally easier to explain when easier for this talk when I talk it using grid lines. And we want to focus on this non-intersecting loop. So if you try to solve this example puzzle, you might end up with something like this. You start with, okay, this is a strike. This white circle is a strike. It must go strike, and it must go to the left because there's nowhere else to go. On a black circle, it must turn, but it must go strike both before and after. So basically, it must go strike for 2 units after that. That is why it cannot go to the right. There's not enough space. So you end up with something like this. And now let's use our corollary. We draw this blue loop, which has one intersection over here. And remember, the intersection with the main loop must be an even number of times. That's what the corollary says. So we need an even number of times. We need one more. But it cannot be here. It cannot be here because the loop over here already goes like this. So there is only one segment remaining. It must be part of the loop. Now, if you look at this, it might look like a very simple deduction. You might not even think about Jordan curve. You might think about just doing cases here. If you go down here, you go to the corner and then get stuck. Okay, sure, but you can apply this in more complicated situations, and often picking the blue loop correctly is the hard part when you have a very complicated puzzle. For example, here, if you continue with this puzzle, you might end up with something like this. Now you can draw this blue loop, which will intersect cleanly. We have one intersection, and then here, this is a white circle. Remember, the main loop is going to go straight through this white circle. In other words, it will not just touch the loop, it will intersect the loop. So this is a third intersection. We need an even number of intersections. That means our remaining one must also be part of the loop, must be another intersection. So you can see how this corollary gets used in more complicated ways. It can make for a very surprising, amazing deduction. And finally, we are going to talk about one last genre called light and shadow. This is not really related to Jordan curve theorem, but it is related to the proof that we talk about. And in light and shadow, the goal is to shade some of the cells black, and each region contains exactly one circle, which will have the same color of the region, and also the number tells the size of the region. So like this T-shaped region is black, it has a black circle, and it has size 4. Now, if you look at the rules of this genre, you might see shade some cells black, but then the rest of the rules say each region same color as the region. I don't really like this phrasing, so sometimes I think about it like this: divide into regions of black and white. Regions of the same color may not be adjacent because otherwise they would merge together into a single larger region. And then the rest of the rules make more sense. And if you think about these rules, divide into regions of black and white and regions of the same color may not be adjacent, this actually comes up in a lot of puzzle games. In Bailetis, in Islands of Insight, in Taiji. Usually these puzzles are about shading some cells black, but then the clues are about the regions themselves, not about the cells. So you can think of these kinds of puzzle games using regions of black and white like this. And there is a very important rule: there is no T-intersections other than along the border of the grid. Why is that the case? Because parity again. See, parity appears again. If you take any intersection like this and then you walk around the intersection, you start from a black region. Every time you cross a region border, you are going to change colors into white, and then another border into black, another border into white, and at the end you must end up where you started. It must be black again, so you must cross borders an even number of times. But a T intersection is three region borders. That does not work. And this result is actually true for any grid, not just squares. You can apply it for triangular grids. You can apply for things like this, tetracase square grid, and so on. The thing is, at every intersection, you must have an even number of regions meeting there. So no T intersection, no intersections of 5. You can have intersection of 4 or 6, but not 5. So if we look back at light and shadow, the rules of this are actually there's quite a lot of rules, even though you think there's not many of them. Let's take a look at a simpler genre. This actually comes up in Bailetis. In Bailetis, you are going to shade some cells black, and then the numbers tell the size of the region. Strictly speaking, this is actually a spoiler, because in Bailetis you are supposed to figure out what the clues do by yourself. But also this is the first clue type that you will see, so I'm like, yeah, whatever. Sorry for spoilers, but also this is the first thing that you will figure out. And when you think about this, shade some cells black, there is going to be multiple solutions, because you can always invert the entire coloring. All the black cells become white, all the white cells become black. It will satisfy the clues as well. And for logic puzzles, people usually don't like having multiple solutions like this. That's why sometimes I think it's easier to phrase it as divide into regions. Well, strictly speaking, divide into regions of black and white and same colors cannot be adjacent, but as we know earlier, it is basically the same thing as no T intersection in the inside of the grid. So divide into regions, there is no T intersection in inside, and then we no longer necessarily have multiple solutions, because inverting the colors just give the exact same regions. Okay, so we end up with rules like this, and if we try to solve this puzzle, let's take a look. These 3 regions have different sizes, so they are different regions, and because we cannot have a T intersection, we must that means the 3 and 1 cannot take the corner. That means the 3 must go up like this. And let's try one more time. The 4 is going to need some extra cell because it's almost closed. These 2 regions, the 3 over here and the 4 over here, cannot become 3. It cannot have a T intersection over here. That means the 4 must take the corner. So that's a way to visualize this. Personally, I find it easier to visualize puzzles like this by treating them as region division puzzle, divide into regions instead of shade some cells black. And when you treat it as regions, you can also come up with rules like this. Note the intersection. I think it's a bit easier to see about the T intersections and so on, rather than using colors. But it is up to you. The important thing here is that it is something that you can derive mathematically. And that's it for my talk. That wraps it up. If you have any questions, we can answer some of them, or you can also ask on Discord. Yeah, thank you.
Thank you so much. I always love these talks. This is the kind of stuff I can never figure out about, like logic puzzles, until somebody shows me, and I'm like, oh yeah, that is how that works. We did get a few questions, and we have time to go through them. So if you're happy to answer a few, yeah, okay, cool. So,
yes.
So first question was from Patrick Trainer, and it's about. So you showed how caves you could represent in two different ways, like using loops or shading.
Yes.
Patrick used the word isomorphic ways to formulate the rules.
Yes.
The question was, how do people choose which way? Or how would, maybe another question there is, if you were also designing a puzzle type, how would you decide which way?
That is a good question. I think for me, I think it's what feels more natural to solve with.
Mm-hmm.
For example, for cave, because of the visibility rules, I think it's usually more natural to say whether a cell is inside or outside the loop. That ends up being the shading.
Mm-hmm. Interesting.
So that's probably something like that.
Great, thank you. It's like which is most intuitive for the given rule set. I guess also for the metaphor of the puzzle, because in caves the metaphor is like the
metaphor is actually more about the loop, I think. Where is it?
Okay, so then we also got a question from Vida, which is, when prototyping and researching math implementations, what resources would you recommend for discovering existing work? Google Scholar, Stack Overflow, or maybe there's more specific resources for specifically maths in puzzles?
That is a good question. I don't think there's like a lot of resources out there. It is because I guess logic puzzles themselves are pretty niche, and it's not too commonly known.
Mm-hmm. I guess we're solving that problem.
Yeah. I guess these kinds of presentations help.
Exactly.
Okay. I remember.
Sorry.
Yes, I remember there was one very new theory that was like discovered, and the write-up was written on a Twitter thread.
Oh, really? Oh no!
And people, yes, it's something really new. Like it's written on Twitter thread, and people are trying to. It was in Japanese as well, so people are trying to translate it. People are trying to clean it up into a blog post or a Google document or something like that to make it easier to read.
Right, but even then, it will probably get lost.
It's hard
as well.
to.
Yeah.
Yes.
Okay, so next question here is from Plush Lola, which is an interesting one. Is why does 2 parity come up so often? Do you have examples of 3 parity, 5, 7, etc.? I kind of remember in your previous talk you were talking about a Monsters Expedition, and that had some.
Monster Expedition had like 4 parity.
Right.
It's 2 parity and 2 parity on each axis, basically.
Sure. Yeah. So I guess what would your answer to like why does 2 parity come up so often?
I think it's because of the concept of different. In 2 parity, there are only 2 things. When you move from one, you must move to the other. Like that. When you move from one, you must move to the other. In 3 parity, you have 3 things. When you move from one, you might end up with one of the other 2. And then from let's say from here, you might you move again from here, you might end up with one of the other two. It's not guaranteed that you are going to cycle everything.
Right.
Yeah.
What was I going to say on? I had something to say on that as well. It doesn't matter. Whatever. So I had a question as well. I'm not sure. Oh no, sorry. Another question came up. Did I miss one? Oh, so Gwen asked, "Does 3 parity come up more in 3D games or hex games?" Interesting.
I don't think so.
Yeah, because it's more about like having 3 options per cell, maybe.
Yes, I cannot quite think up of like any puzzles that naturally have 3 parity, even in hex or anything like that.
So Patrick then followed up that question. On top of that question, what do you think are the reasons why 2D square grids are by far more common for these kinds of puzzles than, say, triangle grids, hex grids, or something else?
I don't actually know that very well. I think it's just because it's just easier to write.
Simple, yeah.
Yes, you have graph paper. It's usually square.
That's
so
very true.
You write puzzles on there. You end up with squares. I
guess that's
just
also
because of that.
That's also connected to the question about like why is 2 parity so common? Well, on a logic paper puzzle, like shading is like a natural thing to be able to do. Like, and then you've immediately got unshaded cells and shaded cells, and suddenly you've got 2 parity. Whereas doing anything more complicated than that requires more complicated annotation, and it gets more complicated. Okay, cool. I think that was all the questions we got, and it's about time for us to set up the next talk. So thank you, Ivan, Chaotic Kayak, for joining us.
Thank you.
And we'll go set up for the next talk.